Hello, this is Graham. It's the 2nd of August, Friday. I'm going to talk about this figure here, which is about Poynting vectors. You can largely ignore the axes. These are the basis vectors. So you have a y, you have an imaginary and a real. So those red and blues are tied to a complex number. But in the context here, what we have is we have an atom, and the electron is going to show you the forces, where the force going inwards, going from the first shell to the ground shell, produces a propagation of an electromagnetic wave. So the electromagnetic wave propagates outwards in the z direction, and it has an imaginary and a real for the electric and magnetic oscillations. And it's the same for these here. So force on the in the z direction, which is this vector here. This is the kickback force as the electron goes along psi z. So she goes from the first shell down to the ground shell and out spits a photon with the same momentum as if this was a moving mass. And using the right-hand rule, left-hand rule, it doesn't really matter. You just have to do it in quaternion form. So what you now have is you have a hop now on the psi y, which does exactly the same. You're going from the shell 1 to this is for a hydrogenic atom, a spherical atom, and so we go on the psi y, which then spits out a propagating wave for this radii. So now we have a circle with the center here, and these are the two radii that are the same. And then we have the next one, which is psi x, and what this does is it gives a ground shell 1 down to ground state and outspits a photon in the x direction. And these three radii will give you a sphere that then grows as it propagates outwards. And I think we've talked about this in one of my videos, but just to be clear here, we are going from force z, which is the Coulomb force, and we're going in a straight line to end up in force z prime. And in order to do that, it has to go through a y and an x to come out as the new z. And this is like the eyelet on a fishing rod, where it gets whipped here, and this is where the line goes through. This is what gives you the helicity or the chirality of how the photon is produced. If we map that not just as a Poynting force, but now looking at how the quarks interact, what we have here is our flat two-dimensional diagrams. But if we take these two and we say that this imaginary is the j-axis, and this one is the I-axis, what you can do is you can do an I cross j, which gives you a new k with a combination of these two. Okay, and that's what gives you the E plus B and the B plus B. So taking this diagram where theta is the probability of time going from here to here, which is obviously a proton or a neutron for the decay or the construction of one. What we're going to do is we're going to have a force that pushes it in that direction, and it is that is the force that's measurable. And what's going on inside in the imaginary is all out of our we don't see it. It's part of space-time that we don't see. And what we do now is we model this, but what we're going to do is we're going to model this as elliptical. So now we have to imagine that the particle is traveling at a certain speed with under a certain gravitational pull, which means that these radii are no longer spherical. The electron is now elliptical in nature in all three spatial directions, similar to a rugby ball that has been stretched and messed around in the third dimension rather than just looking like a rotated ellipse. And the equation for that one is over here, and this is in the matrix form. I've done a video on this, I think. If not, I will do one. And here is the equation that you use, where A and B are the A and B coefficients. There's B for the x, this is B for the y, and this is B for the z. These are the radii that we're looking at, A, and A. So there's permittivity and permeability, and when you do this with the three radii, one is the electric field, one is the magnetic field, what you get is E, which is the size of the lattice. And on a 2x2 lattice for each of these, for a spherical hydrogen atom, you can calculate the spectra and the energy. But if you want to do the elliptical one, something very interesting happens, and this is what gives rise to this image here. And what we're going to do is we're going to concentrate on just this tiny little section here, which is the very, very beginning of the iteration sequence, where the lattices are all set up as initialized to all ones. So there's a tremendous amount of thermal entropy in there, and there is no information entropy at all. And what happens is when billions of iterations are done, this becomes the information entropy, and there is no more energy, thermal energy in there. It's all died away. It's just pure information entropy in there, which is why this is such a good algorithm for doing encryption. But we're going to look at just this little section down here at the beginning. Notice the straight lines. These are the 104 highways in 3 spatial dimensions using 3 independent lattices, but we are using the gyromagnetic rules to transfer the information about where the ant is, and doing the inversion of the dots. And we will look at that over here. So here is this diagram made small, and so this little section right down the bottom here at the beginning, that is all of this. And all of this ends up becoming, this is why I've joined it here, this ends up following this line, and this is where the absolute origin begins, right up here. That's the origin of all of Langton's ants, starting with all the lattices all initialized and ready to go. So this will be literally the first iteration sequence. And the reason why we got these long lines is because the 104 highway, and indeed the creation of Langton's ant itself, is the same on all 3 lattices. So obviously it's going to be a diagonal through all 3 Cartesian axes. There's a kink because at 120 degrees you're going to have one lattice which is now orthogonal to the other 2. And so now, and as you can see, as the lattices start to fill up and they start to show different behavior, you can see that chaos starts to build, and it becomes more and more prevalent. And it's around about here that the system becomes fully chaotic now, because all 3 lattices are E and E-1 and E+1 in size, and so the difference between them is very, very, very small in size. But what's important is that on the long term, that tiny chaos, that tiny little butterfly effect starts to show. And as you can see, it grows and grows and grows and grows, and then it grows even further into 3D here, and then that becomes this, which then, as time goes by, it just explodes into this ball. And this ball in 3D is your probability, which is this thing in 3 dimensions. Okay, and so the actual probability, the area under this curve, is supposed to be of the color, the density, the color. How many times does each of this, think of this as a point cloud that's just connected to each other, and because this is what this is. If you stretch this out really, really far, you'll just find a whole load of blocks next to each other, just like, if I can show you, where have I gone? Here we go. Even I get lost in here sometimes. You can see these aren't actually connected. They're just simply blocks that are next to each other. Same as this one. They're just independent blocks, as I think of it as a point cloud. Okay, where each point has a density and an X, Y, and a Z coordinate. So it's 4-dimensional. Okay. And so this is the Poynting vector. The other way to look at a Poynting vector is to take a surface, and as a photon in this direction strikes the surface, an electron is released. Photoelectric effect. Okay, I think that sums up all of that. There's not much more to say on that one. Thank you very much for listening.